Hello friends, in this video today we are going to discuss about average energy of Planck's oscillator, right? Before we start, please do subscribe to the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel, okay? And if you want to follow me on Insta, this is my Insta ID. This is my Insta ID, OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. And please do subscribe that channel, okay, and hit the thumbs up button, support me to grow my channel, okay. So now let's start. So average energy of Planck's oscillator. Now so average energy of Planck's oscillator, actually what happens here, you see the radiation chamber, according to Planck's postulates, it is considered that the chamber is not only filled with the radiation but also harmonic oscillator, okay. That means it was assumed that black body radiation chamber is consist of simple harmonic oscillator which emits this radiation, okay. So here you see, so here in this video we are going to derive the expression for the average energy of these oscillators, okay. So if we consider n is the total number of Planck's oscillator in a black body radiation chamber, okay, or resonator you can say, and E is the total energy, okay, then average energy, or you can say energy of per oscillator, is E bar by is equal to E by n, right? Let it be equation number 1. Now you see, according to Maxwell's law of molecular motion, number of oscillators having energies. So here I am taking having energy 0 or epsilon, 2 epsilon. Here instead of E I am taking epsilon here because the symbol E already we have used for energy. So here we have considered that the energy of the oscillators are integral multiple of E. E is which is nothing but energy of photon, that is h nu, okay. I will mention that. So these oscillators, number of oscillators having energies are in the ratio 1 is to e to the power minus epsilon by kt is to e to the power minus 2 epsilon by kt dot so on, right? I have considered here like that, right? Hope you have understood this. Now you see here the energy of its oscillator is considered to be integral multiple of epsilon, which is nothing but is equal to h nu. So here epsilon is equal to h nu, right? H nu, h is Planck's constant, nu is frequency. Hope you know this. So where this epsilon is h nu, h is Planck's constant, and nu is the frequency of radiation, right? So now let me take a new slide. If number of oscillators having zero energy, okay, that means 0 times E or 0 times h nu is suppose n naught, let me take it n naught, and number of oscillators having epsilon 1 into epsilon, that means 1 times of h nu, that is suppose n1, and number of oscillators having 2 times of epsilon, that means 2 h nu is suppose n2, and number of oscillators having r times of r times of epsilon, that means r times of h nu is suppose nr, okay, and so on. Then what we can do, we can find the total number n is equal to n naught plus n1 plus n2 plus dot 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 plus rn plus dot 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 so on, okay. Now here you see this n naught plus n1 can be written as n naught times of e to the power minus epsilon by kt. Similarly n2 can be written as n2 times of e to the power minus 2 epsilon by kt. I will explain why, okay, and so on. We can write this way, right? And let me take the n naught common, then we're gonna get this series, right? Okay, now you see, here you see, as I have already told you, the ratio of the numbers, ratio of these numbers, okay, this n naught is to n1 is to, you know, n2 is to dot 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 are in the ratio 1 is to e to the power minus 2 minus epsilon naught minus minus epsilon by kt is to e to the power minus 2 epsilon by kt, right? 2 epsilon by kt and so on. That's why as these numbers are in this ratio, that's why n1 can be written as n naught times of e to the power minus epsilon by kt. Similarly n2 can be written as n naught times into e to the power minus 2 epsilon kt, right, from this ratio as we have already mentioned here, right? So hope you have understood this. Now let me clean this, okay. Similarly you can write nr is equal to n naught e to the power minus r epsilon by kt and so on, right? So that's what we have done. So let me consider these terms. Let me consider this e to the power minus epsilon by kt as y, then e to the power minus 2 epsilon by kt will be equal to y to the power 2, right? Similarly if you take e to the power minus 3 epsilon by kt, then it's gonna be y to the power 3. We can consider that way, right? We have considered here e to the power minus epsilon by kt as y, okay, and taking that way, this series is gonna be of this form. Let me show you in the next page. So n gonna be equal to n naught within bracket, we're gonna get this, okay, where taking e to the power this is equal to y, right? Now you see the series, sum of the series within bracket will be given by this, because you see, let me explain first. Let me explain this, okay. Now you see here, if we apply gp here, first term is a and the common ratio is definitely y, and the sum of first n terms of gp is given by a into 1 minus r to the power n by 1 minus r, right? But for r is very less than 1, for r is very less than 1, this sum equals to, you know, a by 1 minus r. But in this case a is equal to 1 and r is equal to y, so that's why this sum gonna be equal to sum of this series is gonna be equal to 1 by 1 minus y, right? So let me clean these things. So therefore total energy of oscillator E is equal to 0 into n naught, because you know number of oscillators having 0 energy is n naught. Similarly epsilon into n1, because n1 is the number of oscillator having energy epsilon. Similarly 2 epsilon into n2 and so on, we're gonna get this. Then 0 into n naught, that's going to be 0, right? Now epsilon into n1 can be replaced by n naught, into e to the power minus kt. Here epsilon and n naught will be taken common, then within bracket we're gonna get these terms. Okay, right? Hope you have understood this. Now again, this series can be written in this form, right? Using this consideration, right? So then here we're gonna get this result. Let me explain why. As I have already told you, the sum is equal to 1 by 1 minus y for y is very less than 1, because here you see y is very less than 1, y is equal to e to the power minus epsilon by kt. That's obviously it is very less than 1, so that's why we have got this result. So this one into n naught, we have got this expression. Similarly, for y very less than 1, the sum of this series will be equal to y by you see, if you have this series a plus twice a square plus and thrice a cube, then this series is going to be equal to a by 1 minus a whole to the power 2, right? For a very less than 1, right? For a very less than 1. So similarly, in this case we have got this one. Instead of a, we have y, and we have used this result here. That's why we have got this expression, right? Now you see, average energy of Planck's oscillator, that is given by E bar by E by capital N. So let's put the value of E that we have got in the previous slide, that is this one, right? So let me go show you the previous slide, this one. Okay, this is E, and let's put the value of N here, this value of N. Okay, so value of N is this, right? Now if we simplify this here, this one will cancel this, right? So n naught will cancel this one, and then we have got this expression. And then if we put the values of epsilon and y is equal to e to the power minus epsilon by kt divided by 1 minus y again replaced by minus epsilon by kt, e to the power minus epsilon by kt. Now here you see, if we multiply both the numerator and denominator by e to the power plus epsilon by kt, here as well as here, e to the power plus epsilon by kt, then this expression will be of this form. Let me show you. Okay, then it will be equal to this. Let me show you. Epsilon e to the power, sorry, this is going to be equal to 1 minus, not 1 minus, e to the power plus epsilon kt minus 1. Now as epsilon is equal to h nu, let us put this h nu, then this expression gonna be of this form. Let me write this, sorry, just give me a second. So this is the average energy of Planck's oscillator. Okay, so hope you have understood this. Thank you for watching. See you in the next video. Bye bye.